here is the homework 1.4, the back side of the page. We're talking about our word columns. For number 1, we've got a flare, a guy in a boat shoots a flare up straight into the sky. And then we've got this function that models it. So first they want us to graph it. So if I'm going to graph it, I need to know a couple of things. 1, where does it cross the y-axis? And that's going to be at our y-intercept, which is at 4. So I know I have a point here. It'd be helpful if I also knew what the maximum point was for this one, which is what they're asking us to do with B anyway. So I'm going to go ahead and do B, since we're here. I know my highest point of our maximum for a parabola is going to be at minus B over 2A. So for this parabola, that would be minus 20 over 2 times negative 4.9. So that's at 2.04. So approximately at 2 seconds after we launch this flare, it's at the highest height. To find out what that highest height is, though, I'm going to put in 2.04. But in this case, I'm just going to put in 2 so we can get a rough estimate. They didn't ask for anything precise. So I'm just going to put in 2 because that's close to 2.04. Plus 20 times 2 minus 244. Oh, sorry. Plus 4. Can't read my own handwriting here. So I'm taking this 2, which is where my highest point should occur, and I'm plugging it in for 2 into my function. And when I plug that into my function, I get a height of 244 feet. Sorry, that's 24.4 feet. Can't read this. All right, so when x is 2, or when t is 2, we're up here about 24.4, which is going to be really close to 24. And so that's another point. That's my highest point. Now, since this is my axis of symmetry, I know 2 points over here. I should have a symmetrical point on the other side. So my parabola is going to look something like that. So I found my y-intercept, I found my vertex point, and then I reflected this y-intercept across my axis of symmetry to the other side. Now I've got 3 good points, so I can make a pretty decent parabola. Okay, so here's number 2. Now we've got attendance at a state fair. They've got this big function that we're modeling. It says estimate to the nearest relative or nearest unit the relative or absolute extrema and the x values where they occur. So here would be my absolute maximum. So let's go ahead and put that one. Our absolute max, and I'm just abbreviating here. That's about 6,900 people, so an absolute maximum of 6,900 people. And that's on day, let's see, what is that? Oh, approximately on day 7. I also have a smaller little bit of a maximum here, so a local max. At this maximum, we're getting close to 6,000, so 5,900 people. And that's on day, what is it, day 16. Now be careful, because on the quiz, some people, for a graph that looked more like this, they said that there was a minimum or something happened here. But for this one here, it's always decreasing, whereas here we went decreasing and then we increased again to get back to that little maximum. So there is a little minimum here, whereas on like a cubic function, where it's always decreasing, there is no minimum. So here we went down and then we went back up a little bit before we went back down again. So we do have a local minimum. And that's about 5,900 again. And that's, sorry, not at, but on day, what day is that? That's roughly day 13. So in comparison to days 12 and 14, we have a local minimum, but that's a really small one. Well, someone could argue because we have these arrows here, it goes down to negative infinity. But think about this, guys. We are talking about the attendance, so we're talking about people. Can I have negative 500 people or negative infinity people? No. So this has to actually stop at 0. We can't have less than 0. So our absolute minimum, and this makes sense, what's the lowest amount of people you could have? Would be 0 people, absolute minimum of 0 people, and that occurs approximately just before day 2. So I'm just going to say day 2 and a little over day 21, but we'll round it to day 21. So on those 2 days, if we go less than 2 days or more than 21 days, then we have no people at the state fair. I don't know why that is. All right. Number 3 asks us to use that function from number 2 to find some average rates of change. That's a big, gnarly function. First, they want us to find g of 6 minus g of 2 all over 6 minus 2. I'm going to show you how to do the first one, and then I'm just going to give you the answers for the other 2, because really it's a matter of just plugging it into your calculator and getting an answer. So for a g of 6, we're going to plug in 6 into this function, so we've got negative 6 to the 4th plus 48, 6 cubed, minus 822 times 6 squared, plus 5795 times 6, and that should give you, minus 7455. That should give you 6491 people. And then if we plug in g of 2, again, it's just plugging in 2 everywhere you see x. So all these 6's will become 2's. Minus 7455. Cannot say that one. That would give me 1215. Oh, sorry. Once again, reading my notes wrong. This is 6795 people. So again, I'm plugging that in here. G of 6 is 6795 minus the 1215 all over 6 minus 2, which is 4. When you divide that out, that's when you get 6,491 people. It's hard making these videos at the end of the day. I am tired. All right, hopefully that makes sense. Now for B and C, I'm going to show you what you're doing, but you're going to have to plug it into the calculator yourself. So G of 15 minus G of 13 all over 15 minus 13. When you plug in G of 15, you should get 5895. If I'm reading my notes correctly, minus 5857. That's G of 13 all over 15 minus 13, which is 2. And this gives us about rates of change of people over the change of days. So this gives us about 19 people per day. In other words, at this point, if the state fair attendance is growing by about 19 people per day. And then for our last one, we've got G of 20 minus G of 18 all over 20 minus 18. When you plug in 20 into the function, you get 3645. When you plug in 18 into the function, you get 5487. And then 20 minus 18 would be 2. So this gives us negative 921 people per day. So notice for this one, we now have a negative. And does that make sense? It's okay. So if we look between 18 and 20, if it's negative, we should see a lower value on 20 than on 18. So the slope of this guy, does it make sense that that slope is negative? Yes. So that's good. All right, last, but definitely not least, for number 4, we're making a box out of this square piece of paper. A square piece of cardboard, and pretend like that's a square. I'm not a geometry teacher. So there's my square, 18 by 18, and in order to flip up the sides, I've got to cut out a piece out of each corner. Otherwise, when I try to fold up the sides to make a box, they won't tape together nicely. I'll have that little extra piece in there. So what it's saying is, if you take out this corner piece and you cut off a square out of each corner, and each corner length is x, what would the volume be? So if I take x off of this side and x off of this side, this length here, from here to here, now becomes 18 minus 2x. Same thing from here to here, it's 18 minus 2x. So 18 minus this x and minus this x. So my volume now becomes 18 minus 2x, that's one side, times the other side, times my height, which is x. That's the height of my box when I fold it up. So we are folding this paper along these lines, these dotted lines, once we cut out those corners. Now we want to maximize this volume. So in order to maximize it, I'm going to graph it. And when you put this guy in the graph, you're going to see the x value that maximizes it is when x is 3. And that yields a volume of 432. So that's just a matter of plugging this function into your calculator or into Desmos.com and looking at what is the highest point on that. Now you'll see on this graph, I should probably, let's see if I still have Desmos pulled up. So let me see if I can bring it over here because it's worth talking to you about it. Because it gets kind of an interesting graph. Here's Desmos.com. This is what I expect you to use when you're at home if you don't have a graphing calculator, which most people don't, and that's perfectly okay. So if I graph this guy, oh, I don't know what that is. Go away. When I graph this guy, I've got in parentheses 18 minus 2x minus 2x times 18 minus 2x times x. And so here's our graph over here, if you can see it. Notice how it looks a little funky. It's going to be a cubic function, so we should see an absolute value. It's going up, up, up here. And then it's going to reach a maximum value. Let me restrict it in a little bit more, a little bit more, a little bit more. But hopefully you can see that it's going up, and then it's going to come back down. It's going to tank out here at 0, 9, 0, and then it's going to go back up again. But if we want to find our maximum, I'm going to scroll to the top, and I can take my cursor and put it on this dot up here, and that's going to give me the maximum value there. So my maximum value is 432, and that's when x is equal to 3. So that's how I got these values here in B. And then it says, what is the relative minimum of the function? Well, the relative minimum of the function is back down here before. Like I said, it comes back down, and it tanks out here at 9, 0. And so at 9, 0, that's my minimum. And so in the context of the problem, so min value is 0 when x is 9. And I'm going to argue, they call it the relative minimum, and it would be for the overall function. But if we look at the function just in the perspective of just this box, I'm going to argue that's an absolute minimum value. The reason being is, what happens when x is bigger than 9? So if we were to plug in 9 for x here and 9 for x here, how much paper is left over? I don't have any paper left over. Half of it's on this side, half of it's on this side. So now I've got to fold, and I no longer have a box that can hold water. So that's why it doesn't really make sense for x to be bigger than 9. So this would be my absolute value. So when we look at this graph, on Desmos, this part of the graph physically doesn't make sense because x can't be bigger than 9. Just like this part of the graph doesn't make sense because x can't be less than 0. We can't cut out negative numbers out of the side of our box. So you could argue that it's an absolute min, and I would probably accept your argument, and that is your homework for 1.4.